efficiency and all. Today, let us try to compare the enthalpy drops of comparison of enthalpy drop of the reaction turbine and the impulse turbines, which already we have studied. And the impulse turbines. Okay. See, if I take for a reaction turbine, so take for a reaction turbine, the first case, we know that the speed ratio optimum is given by, actually it is U by V1, which was, we derived it as cos alpha 1. Fine. This was the expression. Also, what is the speed, what is the steam velocity speed, or the absolute velocity of the steam is given by, this already we know that V1 is equal to, okay, this already we have this expression 44.72 square root of your enthalpy drop, that is isentropic in the nozzle. This already we have this expression. Now let us equate these expressions. So what will happen if this is equal to, so your V1 is equal to, I can write V1 is equal to U divided by cos alpha 1, which is also equal to 44.72 square root of delta H is isentropic nozzle efficiency. Okay. Or if I take to the left hand side, I can write delta H isentropic nozzle efficiency, that is square root of it, is equal to, K is equal to U divided by 44.72, right? So if I want only delta H square, I have only delta H, I have to square. So I am calling this as equation number. This is for R is equal to 0.5. Let us take, if I take the second case, that is a simple single stage impulse turbine. A single stage impulse turbine. I consider a single stage impulse turbine. Cos alpha 1 by, what are phi optimum or phi max is equal to cos alpha 1 by 2. So now if I try to equate it, okay, what is your phi? This actually it is U by V1, okay. Then if I, what is my V1? V1 is equal to, V1 is equal to your U by 2 times your cos alpha 1, okay. V1 is equal to U by 2 cos. So whatever you had now here, so now this 2 cos alpha 1. I am retaining as 2U1, sir. Is 2U is equal to divided by cos alpha. This is equal to 44.72 into delta H isentropic of the nozzle. Okay. Now, what is the value of delta H if I, same thing if I try, isentropic nozzle is equal to, okay, this will be, I have to take a square, 2 square is 4 into U divided by 44.72 cos alpha 1 square. I'm calling that as equation number 4. This is for a second stage. What will happen if I go for a 2 stages? If I go for a 2-stage impulse turbine, a 2-row or a 2-row impulse turbine, a 2-row impulse turbine. In that case, what will happen? Your phi optimum is equal to, okay, phi optimum is equal to cos alpha 1 by 4. So this is actually 2 into 2. To be very precise, this is actually 2 into 2. So I can write it as cos alpha 1 by 4. Or if I write the same thing for your, so your V1 is equal to 4 times your U divided by cos 1, which is equal to 44.72 square root of delta H isentropic drop the nozzle. Fine. Now if I try to obtain the expression for nozzle, so this will be 4 square, that is 16 into U divided by 44.72 cos alpha 1 square. So this I am calling it as equation number 5. So what is it actually? If you closely observe your, in case of single stage, and it is 16 times your for a two row or a 2-row Curtis or a 2-row input turbine. Okay. Now, what is your efficiency? Efficiency is nothing but your work done by this enthalpy drop. Okay. Now, if you closely observe, so what will happen if you closely observe your efficiency? See, your efficiency, if you closely observe, because when you have the denominator being a bigger number, because your efficiency is equal to work done by your delta H. So with that in mind, the efficiency of your reaction turbine is greater than efficiency of a single stage turbine, which is greater than efficiency of 2-row impulse turbine. I'm looking at quantitatively. Okay, quantitatively, this is how it looks like. Okay. Now, when this is about your efficiency and your enthalpy drops. Let's try to look at some of the numericals and try to understand some of the concepts what already we have learned. So we have a numerical, something like this. The following particulars refers to a stage of a Parsons steam turbine comprising one ring of fixed blades and one ring of moving blades. The mean diameter of the blade ring is 700 mm. The speed is 3000 rpm. The steam velocity at the exit from blade is 160 meters per second. Blade outlet angle is 20 degrees. Steam flow through the blade is 7 kg per second. Draw the velocity triangles or velocity diagram and find the following: blade inlet angle, the tangential force on the moving blades, and the power developed. Okay, this is a problem statement. us write the data what is given. Okay, they are given the mean diameter of the blade, that is D is equal to 700 mm or 0.7 meters, and it is the flow angle that's given. The flow angle is 20 degrees. That is the blade outlet angle with respect to the nozzle, so it becomes flow angle, and which is equal to your beta 2. This being a Parsons turbine, your beta 2 is equal to alpha 1 and beta 1 is equal to alpha 2. Okay. And your speed n is equal to 3000 rpm, and your mass flow rate is equal to 7 kg per second, and your V1 is equal to 160 meters per second. And also, this being a Parsons turbine, my beta 1 is equal to alpha 2. Okay, because my R is equal to 0.5. What are the other conditions we have? VR2. See, VR2 is equal to V1, and your VR1 is equal to V2. These conditions prevail. These conditions prevail in this case of a Parsons turbine. So, what is the first thing you're supposed to do? Actually, we have to find the velocity triangles. Before that, let us find some of the things. So, U is given by phi into D into N by 60. So, it is phi into 700 mm. It is 0.7 into 3000 divided by 60. So, I am getting around 109.95, that is 110 meters per second. Okay. So, now with the given U alpha 1 and V1, I can draw the inlet velocity triangle. So, you can either follow the trigonometric principles or you can go with the graphical method. So, if you want to go for a graphical method, I have to draw to the scale. Okay, I have to draw to the scale, and from the scale I need to, from the scale, say for example, if I take a scale 1 centimeter or 10 mm is equal to 20 or 30 meters per second, something like that. Or I can go with trigonometric principles. So, if I go with my trigonometric principles itself, so let me draw this U. Actually, this is my U, which is 110 meters per second, and with this point I have to draw my V1. So, this is my V1, and alpha 1 is equal to 20 degrees. So, this will be my VR1. So, I can close the triangle by drawing a components of the tangential and flow components. So, this will give my VF1, and this will be giving my VW1. Okay. So, what are those actually? This is my beta. Now, beta 1 will be equal to alpha 2. Also, your alpha 1 is equal to beta 2, because this being a Parsons turbine. This being a Parsons turbine. So, what I will do? So, if I name it, say if I name this as A, this as B, this as C, this as D. Okay. From the point D, I will take a 20-degree line. I'll take a 20-degree line. I'll take a 20-degree line, and what will be actually, that is your CR2, VR2. So, VR2 is equal to V1. So, what is my V1? V1 is given as 160 meters per second. So, this V1 and VR2 both are same. So, this is the point what I am going to get. This will be my VR2, that is my VR2, which is equal to the VR2 is equal to your V1. Then close the triangle. Close the triangle. So what this will be? This will be your V2, and I can draw the horizontal component, that is a tangential component, and the vertical component to that. So this is my VW2, and this is my VF2. The direction will be in this direction. Okay, I got all the components. If you draw it to the scale, you will be getting exactly mirror image of it. So your A, B, C, D, E, yeah. Okay, ADB will be exactly mirror image of your ADE. So both will be same because of R being 1. Or if you want, you can draw to the scale. Graphical method I can use. I can draw to the scale either like something like 1 centimeter is equal to 25 meters per second, and you can find all the things graphic. You can find all the things graphic. Okay. Now this being a Parsons turbine, as I told, your VR2 is equal to V1 and your VR1 is equal to V2. So and alpha 1 is equal to beta 2 and beta 1 is equal to alpha, beta 1 is equal to alpha 2. These conditions are there. Now, first thing what I am supposed to find? Beta 1. So now, beta 1 if I want to find, I can find it graphically or I can find it using your trigonometry. If I want to find the beta 1, what will be the thing I need to do the calculations? So if I take this as x, so x is equal to VW1 minus u. Okay. Let's first find the angle. So if I take the alpha 1, so cos alpha 1, cos, sorry, sin alpha 1. If I take sin alpha 1, cos alpha 1, whatever it may be. If I take sin alpha 1 is equal to, sin alpha 1 is equal to Vf1 divided by V1, or Vf1 is equal to V1 sin alpha 1. So V1 is 160 into sin 20 degrees. So 160 into sin 20, if I do that, I'll be getting my Vf1 as 54.72 meters per second. Similarly, I can take cos alpha 1 is equal to Vw1 by V1, or Vw1 is equal to V1 cos alpha 1, or 160 into cos 20. If I do that, I'll be getting my Vw1 as 150.35 meters per second. I got my Vw1. So what is my x actually? X is equal to Vw1 minus u actually. So or x is equal to Vw1 minus u. So your Vw1 is 150.35 and u is 110. So this is around 40.35 meters per second. Now I'll consider the triangle BCD. Okay. If I consider a triangle BCD, I want to find beta. So tan beta if I take, it will be EVF1 divided by x. So tan beta 1 is equal to VF1 divided by x. Okay. Or beta 1 is equal to tan inverse of Your VF1 is 54.72 divided by your X is 40.35. So beta 1 is equal to 50.5. It is 53.59. 3.59 degrees. See, the same thing if you try to do graphically, see, graphically, you may get around 52 or 53. You may get around 52, 53 graphically if I do the using the graph sheet. This is about your beta 1. So the first part, what we are supposed to find, the inlet blade angle is found. The second thing, I need to find the tangential force. What is the tangential force actually? The tangential force is the mass flow rate into VW1 minus VW2. Okay. If you multiply by your U into mass, U actually you will get the power. Okay. The tangential force. The tangential force is equal to m dot into your VW1 plus VW2. Why I put plus actually? Because your VW1 is in this direction and your VW2 is in other direction. So minus of minus it will become plus. Now if you are doing graphically, just measure the scale from C to F multiplied by 25 meters per second, you may get a value. So roughly around 190 you may get directly. Okay, directly you will get that particular thing and you will get the multiply by your mass flow rate, which is 7, you will get the directly the value. Otherwise, I need to find VW2 here. See, I'm using the trigonometric method, I need to find VW2. Here, VR2 is equal to your V1. Okay, I need to find, and beta 2 is equal to your alpha 1. I can find your VF2. So what I should use? I need to use, let's take sine beta 2. Sine beta 2 is equal to Vf2 divided by your Vr2. And we have beta 2 is equal to alpha 1 and Vr2 is equal to V1. So this condition prevails. So if I substitute, this will become sine 20 is equal to Vf2 divided by Vr2 is equal to your V1, that is 160. So Vf2 and Vf1 both are same, okay, which is 54.72. Okay, 54.7. Now what I need to find? I need to find VW2. If I want to find VW2, I can go with alpha 2. What is your alpha 2? Your alpha 2 is equal to beta 1. Okay, your alpha 2 is equal to beta 1, which is 53.59 degrees. And if I go and look into this triangle, that is, I want to find V. So I can take cos alpha 2 is equal to VW2 divided by V2. Or I can take tan alpha 2 is equal to your VF2 divided by VW. So anyway I can do it. So V2 I don't know. So I can go with your tan alpha 2. So tan alpha 2 is equal to VF2 divided by VW2, or VW2 is equal to VF2 divided by tan your alpha 2 is equal to beta 1. Okay. What is my VF2? It is 54.59 72 divided by 10, 53.59. I'm going to get my VW2, which is 40.36. 40.36 meters per second. Now, what is my tangential force in that case? My tangential force is equal to your mass flow rate is 7 into your VW1 is 150.35 plus 40.36. Okay, 150.35 plus 40.36 into 7. So it's around 1335 newtons or 1.33 kilometers. So I can go with either graphical method also. If you do, you may get around 190 or whatever it may be, or you can go with your trigonometric using the your principles. Now the last thing, I need to find the power developed. The power developed 110. You can divide it by 1000 so that I'll put it in kilowatts. So it comes to around 146.85 kilowatts. So this is the power developed. I have found the tangential force and I have found the corresponding angles, that is beta 1. This is only for degree of reaction R is equal to 0. See, all these conditions R is equal to 0.5. This condition also for R is equal to 0.5, it is valid. For rest of the things, you have to depend on the data. Either I can solve it using maybe you are drawing a simple velocity triangle on a plane sheet and using your trigonometric principles, or on a graph sheet. So either way, you may end up with a similar solutions. Only the numbers may vary at the decimals. Okay, this is about the first part. Let's try to look at one more numerical. Try to look at one more numerical. The total tangential force on one ring of Parsons turbine is 1200 Newton when the blade speed is 100 meters per second. The mass flow rate is 8 kg per second. The blade outlet angle is 20 degrees. Determine the steam velocity at outlet from the blades if the frictional losses which would occur with pure impulse are 25% of the kinetic energy corresponding to the relative velocity at entry to each ring of blades, and if expansion losses are 10% of the heat drop in the blades, determine the heat drop per stage and the stage efficiency, that is your gross stage efficiency. Okay, this is what the problem statement does. Solution. So what is given? So they are given the tangential velocity. So tangential force, that is Ft, which is 1200 Newton, and they have given the blade velocity or your peripheral velocity, which is 100 meters per second, and they have given the mass flow rate, which is 8 kg per second. See, the blade outlet angle, that is beta 2 is equal to 20 degrees, which is also equal to your flow inlet angle. The tangential force, okay, mass flow. and they are given the your VW. See, they are given if the frictional losses which would occur with pure impulse are 25% of the kinetic energy corresponding to the relative velocity at the inlet to each ring of the blades if the expansion losses are 10% of the heat drop. Okay. Now, if I take for example your you have the tangential force. See, you have your tangential force and you. So if I take what are things we are supposed to find? We are supposed to find one is the enthalpy drop, that is delta H per stage, and the efficiency. Now, what is your tangential force? The tangential force is given by tangential force Ft is given by your mass flow rate into Vw1 plus Vw2. Okay. Now, tangential force they are given. Mass flow rate is given. I can easily find Vw1 plus Vw2 is equal to your tangential force by mass flow rate. So this is 1200 divided by 8. So 8 into 150 meters per second. So this is your what we call a VW1 plus VW1. That is the combined or tangential component of the velocity. Okay, this is the tangential velocity of the component. If you now let us draw the velocity triangle. So if I try to draw the velocity triangle, so this is your velocity triangle, and this is my u. Let's go with the graphical method for this. So if alpha is equal to 20 degrees, alpha is equal to 20 degrees, and I can draw this 20 degrees. I can close it. So this is my V1. I need to get the V1. How to get the V1? I need to get the V1. So V1 can be easily found. How? Because the whole thing, see, the VW1 plus VW2, yeah, I need to draw some kind of a graphic. This being a reaction turbine, this being a reaction turbine, the inlet triangle, let me call it as ABC or ABD, whatever it may be. I need to find it based on the blade velocity. So the blade velocity, they given it as 100 meters per second. And I have your alpha. See, I have your alpha, which is, so if I call this as A, so from that particular point, I will draw a 20-degree line. Okay. I know this as, so this particular U as 100 meters per second. So from point, maybe the midpoint. So if I take midpoint, if I take a midpoint, let me take this as a midpoint. I call this as B. Let me call that midpoint as O. Okay. So what is my VW? See, VW1 plus VW2. If you look at it, VW1 plus VW2. The total, if you call this as VW, so to the left hand side, this will be VW by 2, and to the right hand side, this will be VW. I can exactly to the point because this being a symmetric reaction turbine. Okay, so if I call this as say O, what is that number 150? So I'll take 75 meters per second. I can take a scale. You can take a for velocity triangle. I can take a scale. Maybe 1 centimeter is equal to 20 meters per second. If I do that, so 75 meters per second to the left hand side and 75 meters per second to the right hand side. Okay, with O as the center, I will take 75 meters per second. 75, so divided by 20. If I do that, I'll be getting the corresponding and the distance, that is 37.5 mm or 3.75. So from O, I'll take 3.75. I'll take 3.75. So this is actually your 75 meters per second. This is also 75 meters per second. I'll go to this particular point. This is also 75 meters per second. Fine. Now, once I get this point, I'll let me mark that as EB. Let me mark that as C. So if I draw a vertical line from there, this will join. See, this you did not join. See, you can join later. Okay. Now already you have taken this V1. I don't know the value of V1. So just I will draw the V1 at 20 degrees. Now from O, I will take 75 meters per second. That is 3.75 centimeters or 37.5 mm. And I will locate the point C. From C, I will draw a vertical line. So similarly, I will extend this line to this particular point and call that as, so I call this as D. Let me call this as E. From there, I will draw a vertical line. Okay, I will draw a vertical line. Now I know the value of U, so U is already B. So from B, I will join this line. I will join this line. So I'll be getting the beta 1. Okay. Now alpha 1 is equal to beta 2. I will take a line from B. I'll take a line from B and try to, this will be your beta 2, which is equal to alpha 1. This is alpha 1, 20 degrees. So this is my VR1. So this will be my VR2. Okay. So I got the point E. So now once you get the point, you call that as CF. Now join A to F. If you get it, I'll be getting your alpha 2. So I'll be getting, I can measure and get your VF2 and your VW2. This is how you are supposed to get this particular problem. I should be able to get it using the graphical method. Okay. The first, I repeat actually. The first thing, you're supposed to draw the U. You draw, which is 100 meters per second. So that is AB. So mark the midpoint, which is O. From A, you take a line at 20 degrees and extend it. Now you have calculated the VW, that is your tangential velocities, the combined tangential velocity, which is VW1 plus VW2, which is 150 meters per second, and this being a 50% reaction turbine, that is R is equal to 0.5, from mark the midpoint, from the midpoint O, you take 75 meters per second to the left side, 75 to the right hand side on the scale, okay. Then get the point C and E actually, C and E. Then draw a perpendicular line to that. So you draw a perpendicular line, it will intersect at D. So V1, you will get the V1. Then from D, you draw a line to B. So you will get the corresponding VR. Now with beta 2 is equal to alpha 1, from B, draw a 20-degree line. Wherever it intersects, you will get the point F. So from F, you join to A, you get the V2. So then maybe measure the alpha 2 and all the angles, beta 1, beta 2 and alpha 2, you measure and write the angles. Okay. This is about your construction of the velocity triangles. Now, if you try to measure it, so I may get roughly, this is the values you are supposed to get after. So use graphical method. Let me write, use graphical method. Until unless you practice it, you won't be able to get it. Once you draw the velocity triangle, so what are the values you are going to get? So beta 1 is equal to, okay, beta 1 is equal to your alpha 2. Roughly I may get around 59 or 60 degrees. Okay, and your V1 is equal to around 132 meters per second. Your V2 is equal to VR1, which is around 55 to 56 meters per second. You have to get these numbers. Now, what is for a degree, for a R is equal to, for a R is equal to 0.5 turbine, that is R is equal to 50% degree of reaction turbine. The delta H isentropic, for both, see, isentropic for nozzle as well as for the blade, already we have seen, it will be the same, will be VR1 square minus VR2 square by 2. Okay, this is the expression, this is the theoretical expression, let me call that as 1. But what they have told actually in the problem statement, they have told that there is a 25% drop in the kinetic energy. So what should I do actually? Your this particular thing. So your VR2 is actually, it is 0.75 times of VR1. That's the meaning of it. So what I will do actually, VR1 square minus 0.75 VR1 square. 75% drop in that. Okay, divided by 2 into nozzle efficiency. Divided by 2 into nozzle efficiency. What is my VR2? VR2 is equal to V1. VR2 is equal to, VR2 square. VR2 square minus VR1 square is how much? Yeah. And also the efficiency is 90%. They are given nozzle efficiency as 90%, 0.9. Yeah. 10% drop, heat drop, this is the one. So efficiency is equal to 0.9. Yes, it's given. So 90% efficiency. So VR1 square minus VR2 square divided by your 2 times your nozzle. My VR2 square, it is VR2 is equal to V1. So VR2 is equal to V1, that is 132 square minus 0.75 into 56 square into 56 square into 56 square divided by 2 into 0.9. So if I do that, I'm getting around 8,373 joules per kg or 8.37 kilojoules per kg. Okay. So this is for the whole actually. So what is per stage actually? So per stage means, so it is 2 times it of it actually. So this is what is happening in It can be either nozzle or, see, this is, so delta H per stage is equal to delta H rotor plus delta H your nozzle. In reaction turbine, both the values are same. So same values. So what will happen? So the stage will be 2 times your 8373. So it will be 16,000 or 16.75 kilojoules per kg. So this is the enthalpy drop, sorry, heat drop or enthalpy drop per stage. The second thing what we are supposed to find is the efficiency. That's the gross stage efficiency. The gross stage efficiency. So this is given by, so we have done the formula also. Gross stage efficiency is equal to VW1 plus VW2, that's the work done, okay, divided by your delta H for the stage. Okay, so VW1 plus VW2 is 150 into US 100 divided by 16.75 into 10 to the power of 3, because it's 16 kilojoules per kg. So I'll be getting around 89.578. So that is your gross stage efficiency for this particular problem statement. Okay. Yeah, this is about this problem statement.